All right, good afternoon. Today is the lecture number 10. Again, let us briefly recap what we've done last time. Right, so last week we continued our discussion of Maxwell equations in different media. Again, as a remind you, first we've discussed dielectrics, and dielectrics are media that can polarize due to the change of the state of the bound charges, right? So the charges not move like in general through the crystal, through the material, they just deform. They can rotate, they can deform of their orbitals, and all of these changes lead to the appearance of the polarization. And we describe this polarization in terms of induced dipole moment in every single charge, and the net contribution from many charges gives rise to the polarization vector. And of course, if the field changes in time, polarization vector also changes in time, and this is the source of the polarization current in the material. These polarization effects, they describe by this dielectric permittivity, which is a function of frequency, of course. And the stronger the polarization, the larger the permittivity. Okay, so the stronger the effect or the stronger the change of the field in a material, in a medium, the larger the electric permittivity. Yeah, so the electric permittivity, one parameter, another one is refractive index, which is basically the square root of the permittivity. And if permittivity is a complex value, complex function of frequency, which is usually the case because any material has some amount of losses. And there is a theorem that states that if material is lossy, then we deal with the frequency dispersion. So dispersion and loss, they are basically, I mean, one is the reason of another one. Refractive index, real part of refractive index describes how slowly the wave travels through the material, and imaginary part of refractive index describes the dissipation in the material. The larger imaginary part of refractive index, the faster the field dissipates in the dielectric. All right. Dielectric permittivity and refractive index, of course, can be tensors if we deal with materials with some anisotropy, which is quite often the case. Amorphous materials like liquids, like for example, some ceramics, wood, they of course isotropic, but crystal materials, like some crystals, they are anisotropic, and the electric field in one direction causes the polarization in the in general in other direction, and and this all must be described by the tensor. Magnetics described in a similar way. We introduced the magnetic dipole, and this magnetic dipole and net magnetic dipole from many charges leads to the magnetization, M capital here in these formulas, and the magnetization effects are taken into account by the mu, magnetic permeability coefficient, which is also a function of frequency, and it actually depends even stronger, I would say, on frequency than permittivity, because, for example, at optical frequencies and high frequencies, typically magnetic permeability is 1. So no magnetic effects at optical frequencies. Even terahertz frequency range, we also have no magnetic effects. So the presence of dielectrics, conductors in a field can be described by the Maxwell equations that have a similar form to the Maxwell equations in the free space, but changing the epsilon 0 and mu 0 by epsilon 0 mu and mu 0 mu. Right, so the effect of the material of the medium is taken into account in this material parameters. Yeah, so we discussed the case of conductors. So conductors are materials with large densities of free charges, and these free charges in electric field, of course, electric charges move, accelerate, right? And this acceleration of the charges, their movement as a wall creates the electric current. It creates electric current, and of course that electric current then it creates magnetic field, etc. And if electric field changes in time as a harmonic function, we derive this formula for the dielectric permittivity of a metal, okay, like a perfect metal or a plasma. Okay, so the real part of this permittivity is 1, and the imaginary part it gets the imaginary part because of the conductivity sigma, which is a function of frequency, and of course this function of frequency, this conductivity, gets real part and imaginary part. So actually the dielectric permittivity of a metal, of course, a real part, of course not 1. It gets some value which depends on the conductivity. But we don't know what is the conductivity and its function of frequency. There are different models to describe this value, and we consider it the most widespread approach theory, this Drude-Sommerfeld theory, which is all based on Newtonian classical mechanics applied to the electron in a metal or in a plasma. And we derive this polarization and polarizability alpha E for the metal, and this allowed us to derive this simple formula for the permittivity of such a Drude metal. One important parameter here is the plasma frequency, which depends as a square root of density of charges, density of electrons. So the larger the density, the larger the plasma frequency. And in experiment, we observe this plasma frequency or plasma resonance basically as a frequency where the metal transit from not transparent state when epsilon is negative to transparent state when epsilon is positive. Okay. Yeah, so above some frequency, any metal behaves as a dielectric. Okay, so this distinguishing between metals, dielectrics, it always works like you specify the frequency range. Like a metal behaves as a dielectric at higher frequencies. Dielectrics can be ionized and they became like metals also at some higher frequencies. Yeah, and below the plasma frequency, the real part of the epsilon is negative. And even without any imaginary part, which is accounts for the material loss, even without any loss, if the epsilon is negative, then this negative, this minus, appears as I mean in this attenuation law. So it's not dissipation, it's attenuation. The field attenuates inside of the metal. Today we will discuss this a little bit more in terms of the skin effects. Basically, this is the skin effect, or the attenuation of an electric field inside of a metal because of the negative epsilon of the metal. Okay, and yeah, and here is the formula for the conductivity of a metal as a function of frequency. Okay. Then we discuss the boundary conditions. So basically, for Maxwell equations, we derived 4 boundary conditions. These boundary conditions states that the tangential component of electric field and tangential component of magnetic field. Where is it? Yeah, here. Tangential component of electric field, E, and tangential component of magnetic field, H, continues through a boundary between 2 different media. Okay. And the normal component changes because of the difference in the epsilon and mu. Right, so electric field normal component and magnetic field normal component changes by a factor of ratio of mu1 and mu2. I have a sensor in my office, so when I don't move, it turns off the light. So sometimes I need to wave my arm. All right, so yeah, then we concluded this part by writing the Maxwell equations in the general form, fair in a like any material. Okay, and then we started discussing these Maxwell equations in the static and low frequency field, low frequency approximation, and we will continue this discussion today. We started with the static field. Okay, so static field by definition is the field that doesn't change in time. Okay, so in this Maxwell equations, we just assume the time derivative of electric and magnetic field vanishes. At the same time, it means that the frequency of these fields is 0. And since wavelength of the field is opposite to the frequency, the wavelength tends to infinity. Okay, so we derive this or write down this for Maxwell equations in the static regime. in the static regime. For example, for the electric field, we can introduce this scalar potential, because if the curl of electric field is 0, then we can write this curl as a, or the vector of which curl is 0, we can write as a gradient of some scalar field. Okay, so this works only in static. So this formula equals to minus gradient phi, the scalar potential, holds only in the static regime. And in this static regime, one can derive this Poisson equation, which is usually solved in the numerical simulations of static fields, because this is the scalar differential equation for just one component, right? Just one component of the field, just phi, scalar field. And then you can solve this equation in the entire space. And then if you need electric field, you just take the gradient of this solution and you get the solution for the electric field. And then we started our simulations in the ANSYS HFSS, the software, and we solved one or two problems, I don't remember exactly, for the static electric field of a charged, it was sphere, right? So of a charged sphere. Yeah, if you haven't yet, please stop by the computer class and start doing the, practicing the simulations that we discussed. Today we will consider another problem, also to be solved by ANSYS, as an example of the second part. And after the next one, after the next lecture, we will start doing the lab works already in the computer class. All right. So that was lecture number what? Number 9. Number 9. So today's lecture number 10 done. Lecture number 10. And let me, so it was chapter 4, static field. Let me enumerate this one like 4.1, maybe, static field. Then chapter 4 or section 4.2 is going to be quasi-static fields. Quasi-static fields. So what is quasi-static fields? Quasi-static fields means that, yes? Mm-hmm.
I have one question. Sorry for the interruption. But for the previously, you mentioned that electric field equals to minus gradient of the scalar potential. Yeah, what is this scalar potential? What do we mean by this potential?
Just auxiliary function, a gradient of which gives you the electric field. Okay, so this scalar potential, well, it plays two roles. First, it simplifies some calculations, like instead of solving Maxwell equations for all three components of electric field, you just solve one Poisson equation for scalar field and then take the gradient of this field, and it gives you the electric field. This is first. The second purpose of this function is that it is actually the potential potential energy of a charge in this electrostatic field. Okay, so you have some field And if you make an assumption that the charge at the infinity, if you remove this charge from the field, like to the very extent area, if you assign that potential to be 0, then this function, this phi, gives you the potential energy of the charge in such a electrostatic field. Okay, does this answer your question?
Okay, yeah, potential energy of the charge, basically. Yeah.
Yes. So this is the, I mean, with some assumptions, this is the potential energy of a point like charge in the field. Okay, so the quasi-static fields now. Quasi-static fields. So quasi-static fields are fields that change in time, but slowly. Okay, and this basically means that we can omit the terms like the time derivative of electric and magnetic field, comparing to the charge, the time derivative of electric and magnetic field, comparing to the special derivatives of the same fields. So we assume that, or we omit, or the time dependence of the fields, comparing to partial derivatives like curl, for example. Okay, so the partial dependence, like dependence in space, is much larger, stronger than dependence in time. Okay, so it means that fields change in space faster than in time. Fields change in space faster than in time. Or you can say this is the regime of slow fields. So slow fields. So what is the frequency in this region? So the frequency is small. So the frequency is small. And I remind you, omega is equal to 2 pi times f, which is the actual frequency. Okay. At the same time, frequency is equal to the speed of light over wavelengths. So we conclude that the wavelength is large, or very large. So the field that so the field changes very slowly in time, and that means that the wavelength of this field is very large. For example, for the frequency of 1 megahertz, right? So this is the typical frequency of like some electronics. Right? In electronics, the typical frequency is around 1 megahertz. So around 1 megahertz, the wavelength of such a field would be around 300 meters. Right. So the wavelength is very, very large. And what it means in practice, it means that if you compare the phase in one circuit one typical circuit, we would notice no phase retardation due to the field transmission. Okay, so no phase retardation due to the field transmission or propagation. For example, if we have a, let's say, wire like this, and the length of this wire is 1 meter. Wire 1 meter. And if I compare the phase between ends of this wire here and here, so this is the point 0, this is point L. Okay, L is the length of the wire. And if the field changes in time, like cosine omega t minus chi L, right? So there is some phase. So for the first point, cosine k, what would be the coordinate k x? Okay, so x is the coordinate along this wire. So if x is 0, we have cosine 0, which is 1. Okay, and the same time moment, the same field in the coordinate L would be cosine k kl, right? Okay, so cosine k is the 2 pi over lambda, the wave number, and the L is 1 meter. So this is our length of the wire. So let me substitute the 300 meters for 1 megahertz. Okay, so it's going to be 2 pi over 1 meter over 300. So it's going to be something like 0.999, something like that. Okay, so even at the distance between, I mean, in the same circuit over 1 meter, the difference between these two is negligibly small, it's vanishing. And so basically we can or we shouldn't be like care about the phase difference in the same circuit, unless the circuit is like very, very large. All right. At the same time, this allows us to, or make us able to use the lumped element approach. So this allows us to use, or we can use the RLC or lumped element approach, right? This approach works only in the quasi-static approximation. This lumped elements approach of resistors, capacitors, inductors. Why? Because the size of a typical capacitor is maybe 1 centimeter and less, and comparing to the wavelengths, which is 300 meters, it's negligibly small number. Okay, so all the effects that happen in this capacitor or inductor or resistor, they happen like in one single point. Like physically, it is just one single point. And we can like discuss these elements as point-like elements. That's why lumped elements approach. Of course, if you go higher in frequency and, for example, to the gigahertz frequency range, where the typical wavelength is around maybe 1 centimeter or something like that, 3 centimeters, that's already comparable with the size of a capacitor. And at such a high frequency, capacitor doesn't work as a capacitor. The capacitor would work as a bad antenna, because the size of the capacitor of this typical element would be comparable with the wavelengths. And we wouldn't we have to take into account other effects like radiation of the fields from this capacitor, etc. But as long as we are in this quasi steady state or low frequency, as long as we are in this low frequency regime, we can use this RLC lumped elements approach. And I suggest that we discuss the main points about this RLC approach, right? Because it is something that particularly useful for electrical engineers for several reasons. First, RLC approach is the basis for the electronics, for circuit design, right? And on the other hand, RLC approach can be used actually to model some systems that are not composed of RLCs. Okay, so when you have some complex electromagnetic structure system, sometimes you can use the RLC approach. It is known as effective lumped elements approach. You can substitute the actual system by the effective circuit based on RLCs. Okay, and then analyze this RLC system, the circuit, and deduce some information about the actual system. Okay, so this is quite often used in analysis and in designing, and you would be surprised even to modern quantum computers, they are all based on RLC analysis. That's why I suggest that we refresh our mind about this RLC approach, specifically for the quasi-static fields. All right, so the first element, so let us first of all denote this section by 4.2.1, and I name it RLC. So the first lumped element I want to talk about is the simple resistor, right? It can be denoted by this rectangle, or usually it's denoted by this meander line like this. The parameter of a resistor is R, resistance, okay? And in a circuit, this resistance, it gets the voltage drop. So basically we can measure the voltage across this element. If I connect the like a meter and tester to the resistor, it will show me some number because of the finite R. If I have just wire, I use my voltmeter or tester, it would show 0 because the wire is a equipotential surface, right? So if no resistance, then no voltage drop. For the resistor, we have this voltage drop across the resistor, and of course some finite value of the current IR that flows through this resistor. For the resistor, we already know the formulas like Ohm's law, right, which states that the current in a circuit with resistance R is equal to the voltage drop across this resistor over the resistance of this part of the circuit. Okay, or I can isolate the voltage drop from this formula, which is just the product of the current times R. Okay, so R here is the real value, and that in particular means that the phase denoted by this angle, right? The phase of the voltage and the phase of the current flowing through this resistor is the same. So no phase change, no phase delay. So this is the resistance. We already all know about all this. Let me discuss the inductor next. Inductors. So inductor is denoted by this wavy line like this. Physically, it's like a small coil, okay, with maybe some core inside. Essentially, it's a coil. Is denoted by L, inductance. And again, in a circuit, it gets some voltage drop. If I connect it to some power supply or current source, it gets some voltage drop and some current also flowing through this inductor IL. Okay, so how we describe this inductor? So essentially, again, as I said, inductor is a coil, and in the if this current is alternating, the alternating current creates the alternating magnetic field. And when the magnetic field in the coil changes, it induces the electromotive force. Okay, so when B changes, creates electromotive force. Electromotive force, and this electromotive force resists the current and electric field, or the current and magnetic field in the coil. So, and we already know this Faraday's law or Lenz's law for the electromotive force, which is given by the time derivative of the flux of the magnetic field through the through the circuit. Okay. But what is the flux? Flux of magnetic field. Of course, it's given by the magnetic field itself, right? Then by the area of the cross section of the coil, and of course by the number of turns in the coil. So in this case, the electromotive force will be given by minus ns, the time derivative of the magnetic field, of the value of the magnetic field. And we also can note that S is the area of cross-section of the coil. Okay, so the electromotive force is proportional to the change of the magnetic field at time. And magnetic field in its turn depends on the value of the current, of course. Right, this is also something that we very well know. The magnetic field is proportional to the value of the current. And from the experiment, I mean, this proportionality of the magnetic field to the value of the current allows us to connect the flux of the current or flux of the magnetic field with the value of the current, factorizing all the parameters that depend only on the coil itself to the one single parameter, which is L, right? This L, or inductance. So inductance doesn't depend on the current, it only depends on the geometrical parameters, shape and number of the turns of the coil, of the coil itself. Okay, so then the flux of this magnetic field will be given by the product of inductance and the current in the coil. Okay. Hence, the electromotive force in such a coil will be minus L di over dt. Okay, so and so this electromotive force resists to the current and to the voltage of the in the coil, and it is of the opposite sign of the voltage across the coil. That's why we have this minus here, and which states that, I mean, it states for the fact that when the current grows up, the electromotive force is negative. Okay, when it goes down, when the current decreases, the electromotive force is positive. So it always resists to the reason of this current change through the coil. Okay, and for this reason, the actual voltage drop across the coil comes with the opposite sign. So the voltage drop UL is equal to L di L over dt. Okay, so if current is increasing, the electromotive force is induced to reduce the current. If it reduces, then the electromotive force supports the current. So it always resists to the reason it causes. This interesting effect, and it actually gets the interesting connection with the mechanical concept of inertia. You know, this inertia when you sitting in a car or in a bus, and if it gets no acceleration, then you steal. But when it gets like positive acceleration or negative acceleration, it causes you to move because of this inertia. And there is actually a very interesting article by Einstein back to the early last century with this title, like is the inertia is analog to the inductance in the electromagnetism. All right, so yeah, the change of the current through the coil generates the voltage drop across this coil. And this is a quite important formula. Let me frame this formula up. And from this formula, I can isolate the time derivative of the current. So it's gonna be 1 over L UL, right? And if I integrate both parts over time, I'll get the actual formula for the current in transient. It's going to be 1 over L, the integral from like some 0 to moment t, the voltage L, some integration variable theta, d theta. Okay, and plus maybe some constant if the current wasn't 0 in the initial moment of time. Okay. So what else? If my current through the coil is a harmonic function, depends on time as a exponential function. So I is not good. Let me use J. So I use J for the imaginary unit in this section. J omega t. Right. So then the time derivative of current is going to be J omega current. Okay. And hence the voltage drop across the inductor is given by J omega L current. So this is the formula that connects the voltage drop and current through the coil, and it reminds us the Ohm's law. If we denote this coefficient here or prefactor as some resistance, or in this case completely or purely imaginary, so it's impedance, right? So let's denote it by impedance ZL. Okay, so ZL is J omega L. It's another pretty useful formula. It denotes it states that the impedance of the inductor is purely imaginary value. And it's equal to the ratio of voltage over the current. Okay. So on the other hand, if I recall this Euler's formula, cosine alpha plus I sine alpha, right? I use J. I can represent the imaginary unit as what? As a e to the power of j alpha pi over 2. Okay, so cosine pi over 2 is 0, sine pi over 2 is 1. So j is equal to e to the power of j pi over 2. So if I substitute this formula for the imaginary unit to this equation j omega L I L, is gonna be omega L e to the power of j pi over 2 I L. Okay, so we see that this exponential function or factor, it contributes as a phase shift to the current, which means that the phase of the voltage leads the phase of the current. So phase of the voltage minus phase of the current is equal to pi over 2. Okay, so in quadrature, the current and the voltage are in quadrature, and the electric field leads the current. Very good. So this is about the inductance. Let me tell you a few things about the capacitors. Capacitors, right? Capacitor is a system that can store the charge. Is denoted by this this element in the circuits. It gets the letter C, standing for the capacitance, and of course, in a circuit, it also gets some voltage drop across the element, and the current. Of course, current can go through the capacitor if the current is alternating. You remember we discussed already the concept of the displacement current, right? Displacement current can go through capacitor even if nothing between the plates of the capacitor. How it works? So capacitor gets two plates like this, right? And if I take one charge from, for example, from the left plate and move it to the right plate, here we'll get plus, not compensated charge, and minus here, right? And then this plus and minus charges, they are oppositely charged, right? They they attract each other, and if I have more charges like this, all of them attract the counterpart, the opposite charge, and we get this electric field between the plates. Okay, and this system is stable. It can live, like theoretically, can stay in this state forever, and the energy is stored in the system in the form of charge separation. Okay, and if I connect this capacitor to the battery or to the generator, for example, so that in a one-time instant I've got minus here plus here, some of these electrons start flow. I mean, some of these positive charges go here, the negatives go here, and we get current, right? The next time instant, this one is positive, this one is negative, and again, some of these electrons repulse this side and positive to this side. So effectively, we've got this flow of charges, currents, even though we have like an isolator between the between the plates. Okay. If voltage across the capacitor is 0, then current is 0 because of this isolator. When this voltage changes in time, it causes the current in the system. So we conclude that the current through the capacitor is given by the time derivative of the voltage across through the capacitor times some constant, and this constant is known as capacitance. C is capacitance. Right. Capacitance, and from this formula again I can isolate the voltage. It's gonna be 1 over C, right? I integrate both parts, so it's gonna be 0 T I C, integrating parameter T D T plus again some possible constant if the voltage wasn't 0 in the initial time moment. Next, if the voltage depends on time as a exponent, as a harmonic function, j omega t, then again d uc over dt is equal to j omega uc, and hence the current for this case is equal to j omega c uc. And if I again introduce the impedance of this element as a ratio of the voltage drop over the current, right? So it's gonna be 1 over j omega c, or multiplying both parts by j, I get minus and j in the numerator. Okay, so this is another important formula. So again, the impedance of the capacitor is purely imaginary. Okay. What is the phase? What is the phase difference between voltage and current? So we deduce that the voltage is equal to minus j over omega c current. Okay, and what is minus j? So minus j can be represented as e to the power of minus j pi over 2, again because of the earlier formula, and we conclude that the in this case the phase of the current leads the phase of the voltage. So the in the same notation, the phase of the voltage across the capacitor minus phase of the current across the capacitor is equal to minus pi over 2. Okay. Minus pi over 2. And also, so this is for capacitor, inductor, and resistor, lumped elements. For the circuit, of course, we also need the power supply and or like source, and this power supply can be DC, denoted by element like this, the DC power supply in a circuit. It can be AC, denoted by this circle with a wavy line in there, AC. It can be also current source, for example, with the this representation. So it's a current. So you know, current source is a perfect ideal source which supplies the constant current to the circuit regardless of the rest of the circuit. Right. So the current is fixed, or the amount of current is fixed. And we can also, of course, have the voltage source and the power source. So these are all types of sources. So the source drives the current in a circuit, and the purpose or the aim of a circuit analysis is to solve circuit, or in other words, find the currents and voltages in the circuit. And to do so, we use so-called Kirchhoff's laws, right? So to solve circuits, find currents and voltages, we use the Kirchhoff's law. There are two Kirchhoff's circuit laws. Kirchhoff, so complicated name. Kirchhoff's laws. Okay. So there are two Kirchhoff's laws for the circuits. One is known as Kirchhoff's currents law, and it is basically a statement that all algebraic sum of all currents in any node in the circuit is equal to 0. So I take the sum of all currents, okay, in a particular node is equal to 0. Like, for example, I have a node with several wires, currents. This could be current 1, this could be current 2, this can be current 3, etc. And the sum of all of these currents is equal to 0. And so this current Kirchhoff's law is simply a manifestation of the charge conservation law, right? So the number of charges that goes in to this node is equal to the number of charges that goes out from this node. So we can denote it by this, due to charge conservation law. Charge conservation law. This is the first one. There is another one, is known as Kirchhoff's voltage law. Kirchhoff's voltage law. And this is the statement that the algebraic sum of all voltage drops in a loop, in a closed loop of a circuit, also equal to 0. And this is manifestation of what? Of energy conservation law, right? So the voltage is it's connected with the energy, and when I sum up all the energies in the circuit, it leads to the fact that the energy is conserved. All right, so it's I mean, of course, the resistor converts the electric energy to the heat, etc. So it's, but still it's connected to the energy conservation law. So you can also say that due to energy conservation law. Energy conservation law. So I suggest that we describe using, I mean, we use these equations or use this Kirchhoff's law to analyze a simple circuit. Consisting of a generator and inductor, resistor, and capacitor. Okay, so this is low frequency quasi-static field case. We can use the RLC circuits for analysis of it. L stands for the inductance, R for the resistor, C for the capacitance. And we also have this generator, V with the index G, stands for generator. So first what we do, we have to find, we have to define the loop, the closed loop in the circuit. So this circuit literally stands for, consists of just one, or represents just one single loop, right? I can also, I should actually, I have to set a direction of a current. It is auxiliary. Again, auxiliary direction, we can choose, we can set it in a different direction. And also the I have to also set the plus and minus ends of every element in this loop. Okay, so I do it like this: plus minus, plus minus, plus minus, and finally I can also assign this plus and minus here. And then for this given or chosen loop direction, and for the assigned ends of each element plus minus, I take the voltage drop. So I use this Kirchhoff's voltage law, right? And for the if the element, if the direction of the loop goes from plus to minus, then I take the voltage drop across this particular element with plus. If if it goes from minus to plus, then I assign it minus. Okay, in this particular case of our circuit, I have only one minus for the generator, because the loop it goes from minus to plus. So I use I put minus here, voltage generator, and then plus the voltage drop across L, plus voltage drop across R, plus voltage drop across C. It's going to be equal to 0. Right? So what is voltage drop across L? We have the formula here. Voltage drop across L is equal to this formula, right? This formula over here. Or in a general case of any field, of any current, we have this formula, formula in the red frame. So it's gonna be L di L over dt. So this is just one loop, and we have the same current flowing through all these elements. So I remove this index L here and write just current, just current I. Similarly, for the resistor, I have current I times R. And finally, for the capacitance, we have this integral integral formula 1 over C, right? And then the integral from 0 to T, the current that goes through this capacitor. Okay, so I isolate the voltage generator on the left and move everything to the right. And it's gonna be voltage generator is equal to IR for the resistor plus L di dt over for the inductor plus 1 over C integral 0 t I d tau for the capacitor. So now I assume that the current is a harmonic function j omega t, right? So the time derivative of such a current will be given by j omega current, and the integral of this current is gonna be 1 over j omega current. Okay, so I plug in all this to the formula for the voltage integral of the voltage drop of the generator, and when I get IR plus j omega Li plus 1 over j omega C I. Okay, I don't like to have this imaginary unit in the denominator. I move it up and put minus here. Okay, and now I factorize the current. So I get R plus j omega L minus 1 minus j omega C times current. Again, the ratio of the voltage over current is equal to some sort of impedance, right? So voltage over the current, in our case, it's equal to R plus j omega L minus j omega C. And I also want to factorize this imaginary unit like this. Okay, and this is equal to the complex impedance of a circuit. So it's a complex impedance of the circuit. Complex impedance. So this impedance is complex number, and complex number described by the amplitude and the phase of the complex number. And for the amplitude of this complex number, oh, well, we know this formula, the square root of real part of complex number plus the imaginary part of this complex number squared, and I take the square root of it, right? So in our case, this absolute value of the complex impedance of the circuit is gonna be equal R squared plus omega L minus 1 over omega C squared. Okay. The absolute value of the complex impedance of the circuit. So now, let me ask myself the following question: what is the for the given voltage of the generator, what is the or when is the maximum current? For what parameters I would get the maximum current in my circuit? So for the given for the given generator, when I get the when is the max current? Okay, so the current is equal to the voltage over the impedance, or absolute value of the impedance, because I'm worrying about the absolute value of the current. And it's equal to voltage over square root of R squared plus omega L minus 1 omega C squared, right? And when is the maximum, or what is the maximum value of the current? The maximum value of this current would be when the denominator is smallest, right? And the numerator is smallest when this guy is equal to 0. So I is max when omega L is equal to 1 omega C. Or from this I conclude that omega is to be equal to 1 over square root of LC. So this is famous Thomson's formula for the resonant frequency of a resonant circuit. Okay, and when it happens, this I max is equal to generator over R. Okay. At the same time, the power that the real part of the power, the active power in the circuit only for the resistor, right? The power that dissipates in form of the heat. So the real part of the power in this circuit is going to be given by the product of the voltage across the resistor times the current in the resistor, which is the same, current for all these elements. Or since the voltage drop is current over R, we get this current squared over R, right? And we conclude that for the given R, the voltage, the power, the active part of the power is maximum when at this resonant frequency. Okay, so the power is maximum when omega L is equal to 1 over omega C. So, or in the resonant case, resonance. So this is the manifestation of a resonance. At resonance, the reactive parts, they compensate each other. For example, in our case, the reactive part of the inductor compensate the reactive part of the capacitor, and so this imaginary part of the input impedance is 0, is gone, and the complex frequency turns into a real a real number. It is seen from this formula here, right? At resonance, the complex impedance of a circuit becomes real valued, and in this regime, we have no energy storage in the reactive elements. So we don't lose energy for the reactive elements, okay? And all energy, or the maximum of energy, is is converted to the active part. Okay, so active power is the power or energy that can do something, like convert electric field or electric current to the heat, or I mean, whatever, do mechanical things, etc., and so on and so forth. And it is crucial that in such cases, or typically, we like get rid of this reactive part of the impedance of the circuit to increase the efficiency of the circuit. And this is known as the impedance matching. Impedance matching. So we design the circuit in a way that it is matched with the generator. Okay, so the generator supplies the maximum amount of energy to the circuit. All right, so we are running out of time. Let me transit to the eddy currents effect. So let me repeat what we've discussed so far in this lecture about quasi-static fields. So the quasi-static fields, the fields with very large wavelengths, and this fact that the wavelength is very large means that we have no phase retardation for the wires, for the conductors, for the typical wires. Okay, and at the same time, all the elements in the, for example, in the circuit, much smaller than the wavelengths. And since we have no phase retardation, no phase delay between the points in the circuit, we can discuss, or we can consider each element of the circuit as a lumped element with basically like a point-like element. Okay, so we don't consider different radiation effects, like or mutual communications or mutual interaction of the elements. So the elements just point-like elements, and we can describe them in terms of RLC circuits, RLC lumped elements, resistors, inductors, capacitors. These are just linear elements. Of course, we have other elements like nonlinear elements, like diodes, like transistors, thyristors, varactors. All of them are nonlinear elements where the voltage or current depends nonlinearly on voltage, and these nonlinear elements open up a lot of functionality, right? In fact, all the computers, any circuits, basically, they include such nonlinear elements. And also we have active elements. Active means the element with negative resistance. So negative resistance works as a generator of energy. It, instead of absorbing energy because of the Joule's law, it generates energy because of this minus, right? And all these, I mean, elements, they bring new functionality to the circuits, and they can be also analyzed in similar way. Here we just describe this linear passive elements of circuit analysis. So let me tell you about the eddy currents next, because this is another manifestation of the quasi-static fields. Okay, quasi-static fields are fields that change slowly in space, and this slow change in space of the field, and at the same time slow change of the fields in time, it leads to this another peculiar effect known as eddy currents. Eddy currents. So 4.2.3 eddy, or 2, sorry, 2 eddy currents. So we recall today that the field decays in a metal because of the negative epsilon, negative permittivity. Okay, if conductivity of a metal is finite, then the permittivity is also negative. It can be very large, but still finite. Finite negative permittivity. And at the same time, it means that the field still penetrates to the metal by some amount of, by some distance. And this distance is known as skin depth. Okay, skin depth. At the same time, the conductivity of a metal strongly depends on the frequency. And usually when the field is very slow, like almost static, it doesn't cause any problems, because if the field is very slow, then the change of this field, like very slow change of this field, creates a very weak current in the metal. Okay, so it's not a problem for static fields or like almost static fields. When the field changes very fast, like in optics, in that case, the skin depth becomes very small, like maybe 100 nanometers or even less, and the field literally doesn't penetrate inside in the metal, and doesn't also cause any noticeable problems. And this point about the eddy currents is mostly important in the case of the low frequency fields, like 1 megahertz frequency field around. Okay, so what is the eddy currents? So let us imagine, or let us consider a piece of metal like this. So this is a metal, or metallic slab. Okay, metallic slab. It can be copper, aluminum, whatever. And then I have a coil, let me actually maybe move this part down a little. Okay, and then I have a coil like this. Okay, and this coil, of course, creates the magnetic field. And if the current in the coil is alternating, then this magnetic field also alternating in time. On the other hand, we know this Maxwell equation that the curl of electric field is given by the minus dB over dt, right? So the change in time of the magnetic field creates the curl of electric field. And of course, because of the finite skin depth in the metal, it creates also the curl of electric field inside of the metal. Excuse me, do you have any questions, Marco? If not, yeah, please keep mute yourself. Right, so the change of the magnetic field in time creates the curl of electric field. The B in time creates a curl of electric field. It's the curl of electric field. Right. So next, if the conductivity is finite, then the electric field creates the current, right? Induces the current according to this local Ohm's law. And hence, if I, for example, isolate electric field from this formula and plug into this one, I come to conclusion that the changing of the magnetic field in time creates the curl of electric field. Time creates curl of current, and this curl of current is, and of course, orthogonal to the magnetic field, and proportional to the conductivity of the metal. It is exactly what we know by the eddy currents. Okay, so I don't want to like derive any formulas here. Instead, let us go to ANSYS HFSS and simulate such a system. Let me launch the ANSYS and share my screen. Okay. So guys, do you see the window, this ANSYS HFSS electronic desktop? All right. So how I do this simulation? Again, I go to the Maxwell solver, right? And then I go to the Maxwell 3D and select solution type. So last time we discussed that we've got these 7 different solvers. The second one, I mean this one, electrostatic one, we discussed last time. Oh, something happened to my. Do you see my screen?
Yes, we can see it.
Oh,
What is-
interesting. Okay, okay. All right, so this time we select this AD current solver. So first of all, we need to draw the metallic slab. Okay, so I draw the box in the XY plane like this, and give it some thickness. So my metallic box, metallic slab will be made of copper. So I go to the material search and find copper. Okay, and change the color of this copper to the copper-like color. So now I change the position of this slab to let's make this slab with the size of 100 millimeters, 100 millimeters, and 220 and 10. Okay, so it's gonna be 50 here, 50 here, and minus 20, or yeah, minus 20 here. X size 100, Y size 100, and Z. Let's make it 10. Okay, apply. Okay, and then fit all. Okay, so this is the that's fine, I guess. Yeah. So metallic slab made of copper. So next step is to create a coil. And in order to create a coil, I draw a cylinder with the base in this XY plane oriented along Z direction, like this. So this is the outer surface or outer area of the coil. It's gonna be the coil actually, and in order to make it looking like a coil, I need to draw the inner area here, like this. Okay, and subtract the second one from the first one. But before that, let me so the outer gonna be maybe 15 millimeters, and the inner gonna be, for example, let's say 12 millimeters, 50, height minus 50, and here 0.50. Let's make this one 0, and this one plus 50. Oops. Plus 50. So they like oriented the same way. So now I have to highlight both and go to the Boolean operations and subtract. Okay, so I subtract the first one from this. No, I subtract the second one from the first one. Is that right? Yes. Okay. So this whole cylinder gonna be the coil. So in order to make it a coil, first let's change the material of this one also to copper. Okay, so our coil gonna be made of copper. And now we need to assign or make a winding, right? The actual coil. So in order to do so, I draw the no, actually I can highlight this cylinder. Is it? And oops. And then excitations, add the winding. Okay, winding, and then stranded. And let's assign it a current of 1 ampere. Okay, very good. And now in this winding, we need to assign coil terminal. Okay, so this is basically how the coil is excited and arranged. To do so, I select a plane, for example, this one, and then I draw a rectangle in this plane. Like this. Right. Yeah, so this is the terminal of the coil. And I need to assign this. So as I go to windings, assign the coil terminal and give it number of conductors. So let's make it maybe 100 or so. So this is n in our formulas, the number of turns. Okay. So what's next? Of course, I need to draw the region around the structure. Let's make it maybe 100% of the structure size. Okay, so it's region around. Let me hide this region from the monitor, so it doesn't interfere with the structure. So what else? Analysis, right? I need to create an add solution setup. Let's make number of passes 10 and the percent error to be 0.1. Okay. I can also change the mesh, but for let's make it. No, actually, let's keep it is the default number. And yeah, I validate the simulation. We have no boundaries here, but that's fine. That's okay for this project. And I go ahead and analyze all, save the project, and run the simulation. Okay, so in a few minutes, the simulation is gonna be completed. And let me tell you what we expect to see, right? So this coil, vertically oriented coil, creates the vertically oriented of magnetic field. And this magnetic field penetrates inside of this metal. This metal, the copper, it has no magnetic permeability. So for the magnetic field is like a vacuum, like nothing here, okay, because no magnetic effects. But at the same time, the fact that magnetic field alternates in time, this alternating magnetic field creates the curl of electric field inside of the metal too. And since the metal gets finite conductivity, the curl of electric field induces the curl of the current inside of this metal. And yeah, and this curl of current alternating in time because of the finite conductivity creates the dissipation, right? Dissipation of the electric field, dissipation of the current in the metal, and turning it into heat. That's why these eddy currents they harmful for different systems, like for transformers and for other systems, but sometimes they are useful. For example, in these heaters where we use eddy currents to heat and actually melt the metals. All right, so my project is executed, and let me first see the magnetic field in this ZY plane. So as before, I select this plane, then right click on the window and navigate to the fields and select this magnetic field in the vector form. Okay, by default we've got this 60 hertz. Of course, we can design it, redo the simulation for the higher frequencies. So I select this vector field and click done. Okay, and it creates the magnetic field. So we see that the presence of the metallic slab actually changes the distribution of the magnetic field. So it is not really like nothing, right? Not empty space. Why? Well, because as we will see now, this metallic slab gets the eddy currents. Eddy currents, they are currents, right? These currents also create the magnetic field, and this magnetic field and the superposition of these magnetic fields from the eddy currents with the magnetic field from the coil basically leads to this this change of the magnetic field in the area. All right, so now I need to see the eddy currents at the surface of this metallic slab. To do so, I navigate to draw and select the face and click this face, upper face of the metallic slab. Okay, and now in this regime, in this null mode, I right click on the window and navigate to the fields and to the current and vector representation. Done. Okay, so this is the vector distribution of the eddy current at the surface of the metallic slab, as you can see. So this is static now because it is time instant. I can go to the window or to the view and click animate, select vector or the current, doesn't matter, and run the animation. Okay, so now it is animated, and now we can nicely see what happens to this system, what happens to the current distribution, and how it follows the magnetic field. For example, when magnetic field points up, the current is clockwise. When it goes down, the current is counterclockwise. Yeah, but this is the current on the surface, right? But what happens in the bulk? What happens in the bulk of this metal? In order to test that, I select the orthogonal space, orthogonal plane, okay, and in this orthogonal plane, and in this mode, I go to the current and the magnitude of this current in this plane. So I see nothing here because because this metallic slab is not transparent. We can make it transparent, or actually hide it from the screen like this. Do I see anything? Not really. Let me remove the magnetic field. Aha, so it's there. I just don't see it. Let me reduce the maximum value of the current, like this. It's too much more here, and maybe 3 here. Anyway, so yeah, this is this basically conveys my point. As you can see, the current not only distributed, this eddy current, not only on the surface, but it also penetrates inside, right? So we see this current distribution inside of the slab. And at the same time, it decreases as we go from the boundary, right? We clearly see it here. The current is decreasing when we go from the surface to the bulk of the metal. And this is manifestation of this skin depth effect. Okay. Yeah, so this is basically what I wanted to tell you today. Let me stop the share and stop recording.